Hello everyone, the problem we chose was problem C, birds of different feathers. My name is Mark.
I'm Norah.
And I'm Alexis.
Our coach is Dr. Kimberly Williams, and we're at Duquesne University. Scientific literature shows that groups of mixed prey species have reduced predation risk as a result of possible advantages including increased grazing efficiency, better dilution, and better detection of predators. With the similar problem that our group chose, we were tasked with developing a mathematical model to understand the effect that groups of vigilant prey have on their survival. With our model, we explore how the number of different species present will affect group survival and observe the dynamics of our prey populations.
In order to develop a model that determines the impact of prey grouping on the ability to detect predators, we had to make a few assumptions. We assumed that this would be a low-risk environment with moderate population density. Our model only consists of one predator species, specifically lions, that target all prey species equally. We also assumed that all prey species behave the same in terms of growth rate, vigilance, and alarm, allowing for the prey to be grouped into one large equation. Vigilance impacts prey and predator at the same rate in our model, and the addition of more prey species to the group will change the group vigilance. Based on those assumptions, we developed a model that measures the ability of a group of mixed prey species to detect a predator based on prey populations, given that more prey will survive if they can better detect predators. Our model is based on the Lotka-Volterra model with alterations to fit this scenario. X represents the prey population, including all added species, and the Y represents the predator population. The carrying capacity serves as our mode of competition, given that as the number of prey species increases, there is still a constant limit to the amount of prey that can survive. Predators are assumed to only die of natural causes, which is represented by the death rate delta. Mu is introduced, which incorporates group vigilance, which changes based on the number of prey species. Given mu represents vigilance, it equally dampens the impact of alpha and beta on both the predator and prey population. To introduce the multi-species component of our model, our prey vigilance function changes based on the number of prey species at any given time. We have a group vigilance function denoted by mu and an individual vigilance function denoted by sigma. Individual vigilance decreases due to the dilution of prey, and the function at which it decreases was based on data from literature that shows vigilance of individual prey as a function of group size. We plotted this data and achieved a function that we then altered to fit our data by changing the initial value to 0.09 to reflect the vigilance of a single species in a low-risk environment. Group vigilance increases as more prey is added based on individual vigilance, the number of prey species, and alarm, which is the likelihood of the prey communicating a predation risk. This function is added to the initial group vigilance with each additional species. Our ODE 15S function was called first within the loop, where each iteration of the loop represented n number of prey species within the prey group. The xn function represents the initial value of prey called within the ODE function that changes for each iteration, where at n equals 1 it would be 6 given that it is a group of only zebras. The addition of 12 at each iteration considers that members of the new species must be included at each run of new iterations, and mixed species groups include approximately 12 non-zebras. The group vigilance then changes based on the new number of species but cannot exceed or match beta, given we assume that predators' only form of growth was via prey consumption, so beta minus mu must be positive. If mu exceeds beta, it will be reset to a value just less than beta to ensure a positive growth rate for predators. Our ODE 15S pred-prey function returned the data after each iteration, so the prey population could be measured at each number of prey species within the group. All parameter values were obtained from literature based on the interaction between lions and zebras. These parameters held true for our model given that we assumed all prey species behave like zebras. Alpha was determined given that 17.5% of zebras are killed by lions annually, and beta was found from the fact that 15% of lion kills comprise zebras. Zebra populations grow at a rate of 22.3%, indicating the gamma value. Delta was decided given that 16% of lion deaths were found to be natural causes. A carrying capacity was determined given that a moderate density environment typically contains 500 to 1,000 zebras. The initial vigilance values were based on the vigilance of single species in a low-risk setting, but changes as more species are introduced. Zebras were shown to form groups of 6, and lions formed groups of 8 to 13, which influenced our initial prey and predator values.
Using this model over a scale of 10,000 time units and with a carrying capacity of 500, we can see the resulting relationship between population of predators in red and prey in blue for each additional species added. The n value at the top of the graph is the amount of species grouping together. As I flip through these graphs, we see that as more species group together, their population does increase before evening out once an equilibrium state is reached. And there we can see the change in the amount of prey and how the amount of prey at the equilibrium becomes consistently higher than the amount of predators until we reach n equals 7, where the prey population stays at a constant amount above the predators, acting as the upper limit for the beneficial number of species grouping. And here's all the graphs together where we can see the trend of increasing prey until about n equals 7. This graph shows the minimum, maximum, and average prey at the end of a long period of time, where we can see the increase in prey population due to greater survival rates with grouping. Again, it is visible that having more than 7 species is not necessarily beneficial because the increase in prey reaches a maximum. This graph is similar, but shows the average populations over the whole time scale for both prey and predators with each additional species added. To see how our model functions under different circumstances, we vary parameters to exemplify different modifications to the environment. The graph on the left shows the resulting average populations when the carrying capacities increase from k equals 500 to 1000. The initial and final amounts of both predators and prey are increased, which is to be expected. The exponential nature of the curve is slightly decreased, likely due to the fact that the growth factor can have a greater effect on the prey population until it plateaus. Then the carrying capacity was decreased to a value of 100. The initial population averages were decreased in result, and the exponential curve was amplified due to the reverse of the previous reason. Then we decreased the predator death rate from a value of delta equals 0.16 to 0.1. We found that the predator population did stay above the prey for the first few prey groups, but as we get to around 4 grouped prey species, the prey is able to outweigh the predators again. As the prey group together, our mu value, which is group vigilance, continues to increase until it outweighs the lack of predator death, meaning you would need minimum more species grouping for it to be beneficial to the prey. The effect of prey consumption on predators was also varied from beta equals 0.15 to 0.1, exemplifying a decrease in growth rate of predators. Resultingly, we find an increase in prey population and decrease in predator population, and the predator population is fairly unchanging, while the prey reaches its plateau at 3 species groupings instead of 7, meaning that when the predators are not increasing as much, the prey don't need as high of a group vigilance to outweigh them.
Overall, since we observed an increase in prey population size and a reduced amount of time to reach an equilibrium solution as we increase the number of different species, we can conclude that groups of prey that group together are likely to better detect predators and continue to live on. As for answering the importance of the number of species for survival, we determined for there to be a non-trivial advantage, there must be at least 2 members of each species so that they are each able to repopulate. Otherwise, the final prey population size that we observe will not include species of prey originally found within our initial condition. From our data, we saw the fulfillment of this condition at n is equal to 7. We also see that after that point, our final prey population size no longer increases as we increase the number of prey species, thus n equals 7 is also our upper limit. One limitation of our model is that with our generalization of prey into a single equation, we're unable to see the dynamics of each individual species. By including more equations that each represent a different prey species, we can not only see the decomposition of the generalized equation, but we could also individually change each species' interaction with one another in order to get a better portrayal of the uniqueness of each species. Another concept that could be further explored and was briefly addressed by our model would be the negative effects of prey grouping together, which would mainly be competition. For our model, we limited ourselves to carrying capacity. However, if we were to implement the previous improvement and incorporate terms that dictate the relative competition of each species, we could further assess whether our findings still hold to be true. Lastly, our model simplifies that all the different prey species are friendly and will respond to the alertness of other prey. However, if we were to consider factors such as competition, it's possible that the species of prey that are suffering from competition will be unresponsive to the alertness of other prey because they would be too focused on recuperating food for survival.
Thank you! We hope we dazzled you away.